Welcome, everybody, and thanks for registering for today's webinar. I am Marty Major from the Sales Enablement Training team, and I'm here with Jerry Beanie, who is our Director of Global Business Development for our R&D and Science and Automation team, and he's going to be the primary presenter here today discussing what you can see here on your screen. How thermal imaging empowers manufacturers to overcome the global microchip scarcity problem. As always, in the GoToWebinar platform, you can use the questions section on the overlay on the right-hand side to ask our team of experts any questions you might have as Jerry is presenting. Keep in mind that at the end of this webinar, we will have a questions section where Jerry and his team will answer your questions live. So sit back, get comfortable, and let's get ready to learn. Jerry, go ahead and take it away.
Thank you, Marty. Hello, everyone, and welcome. It's my pleasure to speak to you today on behalf of Teledyne FLIR's R&D and Science segment. I appreciate everyone taking the time out of your busy schedules to meet with us for the next 45 minutes or so to really learn how thermal imaging can help manufacturers save money and strengthen their supply chain for electronic systems and components. As everyone knows, the worldwide supply of semiconductor material and microchips was heavily impacted by the lockdowns and labor restrictions resulting from the COVID-19 pandemic. At the beginning of the pandemic, there was a sudden drop in manufacturing due to a lot of canceled orders and some adjustments in the overall supply chain. However, at the same time, demand for microchips actually rose as work from home practices increased with the use of laptop computers, cell phones, gaming systems, and actually other IT equipment. So by the third quarter of 2020, the demand for semiconductors had surged globally. However, the increase in demand coupled with limited production capacity caused significant disruptions for many manufacturers, really leading to some factories closing and affecting hundreds of industries worldwide. Really everything from medical devices, smartphones, and telecommunications to really aerospace, defense, and heavy machinery were impacted as a result. In fact, according to research by Goldman Sachs, about 169 different industries worldwide were affected by the widespread microchip shortage. As an example, the automotive industry, which by itself accounts for roughly 10% of the global semiconductor market, experienced well-publicized delays. The UK alone experienced a sharp 30% drop in production compared to pre-pandemic levels, while purchases of new cars were down 25% globally in 2022. This even had a ripple effect on the used car market as a limited supply of new vehicles resulted in prices for used cars just skyrocketing. I actually experienced this firsthand when I needed to purchase a used car for my college-age son during the summer of 2022 and saw prices that were 50 or sometimes 100% higher than their kind of real market value was. But this is just an example of one industry. The global impact of the semiconductor and microchip supply chain shortage was and remains pretty significant. But the semiconductor market was fragile actually long before COVID-19 and the government shutdowns. In actuality, a series of different events over a number of years combined to create the chip shortage. As you can see, the events included a well-known trade war between the US and China that impacted commodity pricing and distribution. There were natural disasters like the drought in Taiwan, which was significant since semiconductor manufacturing actually uses a lot of water. And there were the winter storms in Texas a couple years back that damaged some major factories. There were even fires at 3 separate plants in Japan between 2019 and 2021 that devastated operations and contributed to some raw material shortages. All this reduced production capacity as the demands grew globally. And even as many of the semiconductor suppliers work to build new facilities and expand capacity to meet demands, they still expect the shortages to continue into the years to come. In fact, a recent survey by the European Commission forecasts that by 2030, demand for microchips will double, further adding pressure to manufacturers using semiconductors across all industries to diversify and strengthen their overall supply chain. In an effort to increase the supply of semiconductors and reduce their dependency on foreign governments for critical digital infrastructure and boost local economies, many major governments around the world are actually racing to build chip plants at home. To accelerate the process, governments from Washington to Seoul have been offering incentives for domestic chip production in hopes of reducing their heavy reliance on foreign suppliers like Taiwan for advanced semiconductors and avoiding future supply disruptions. In the last year or so, both the US and European Union have enacted legislation and activated billions of dollars in funding to empower regional businesses to generate homegrown semiconductors rather than source them overseas, with the hopes of resolving those future supply chain disruptions at the source. The US CHIPS and Science Act of 2022 directs about $280 billion in spending over the next 10 years. The majority of the funds, roughly $200 billion, are specifically slated for scientific research in semiconductor development and commercialization. Another $52 billion is earmarked to bolster onshore semiconductor manufacturing and workforce development, while another $24 billion is being set aside for tax credits for chip production facilities. The EU CHIPS Act also is a piece of legislation that came into force in July this year, which is designed to encourage innovation in microelectronics and actually increase the EU's share of the microchip production they want to get to about 20% in the next 7 years. Linked to the Act is really a vehicle to access the funding, otherwise known as the Important Project of Common European Interest in Microelectronics and Communication Technologies. The Act and project combine to create an immediate incentives for European companies to shift focus from externally sourcing vital parts of the machinery to producing them in-house, with the necessary support and funding to make it happen. Beyond the initial pledge of 1.8 billion euros in state aid, the move is also expected to unlock a further 13 to 14 billion euros in private investments across 14 different member countries, which include Austria, Finland, France, Greece, Germany, and others. And so far, 68 projects have been pledged across 56 companies, including global brands such as Vodafone, Infineon, Ericsson, and Global Foundries. So how can Teledyne FLIR thermal cameras help in these global efforts? Well, whatever the scope of these ambitious projects and whether chips are being used to capture, process, store, or act on data directly, testing will be vital in the development process. To get the most from the available funding, companies will need to be able to test their components to meet specific safety standards. Whether it's testing functionality, performance, or quality assurance, the electronic components will need to be carefully vetted. Thermography actually plays a vital role in allowing manufacturers to monitor their circuitry to detect heat dissipation or thermal runaway as it develops. Observing the thermal characteristics of their microchips in real time will actually ensure that any issues with implementation or the compatibility of components are spotted and treated early on in the process, preventing costly downtimes and really shortening the design cycle to make it as efficient as possible. As you can imagine, thermal imaging and non-contact temperature measurements can be a valuable testing resource in a lot of different parts of the electronic component's life cycle. In the design phase, thermal imaging can be used to evaluate individual components and the temperature values that can be used to validate CFD models. They can then be used to better understand the thermal dynamics of the entire system once assembled and how it performs in real-world conditions. And if by chance something fails during the testing, thermal imaging can be used to help determine the potential cause of the failure and verify any necessary repairs when done appropriately. But it doesn't just stop upstream at the design and testing and repair. Thermal imaging and the valuable information that it provides can also be used during the manufacturing process of the electronic devices and systems. If you think about it, if you use thermal imaging to ensure product design and quality in the design phase, doesn't it make sense to also do it at critical points in the overall production process? And with the global push for green energy and improved energy efficiency in the systems we use every day, it's important for designers to evaluate how radiant heating from the systems can waste energy. And it's getting increasingly more challenging as designers are being asked to deliver more and more functionality on smaller and smaller package sizes. And think about it, with an average of over 1,500 microchips in a typical electric vehicle, even very small energy savings per device can add up to significant improvements in efficiency and performance. Efficient electronic systems mean less power is wasted as heat, and thermal imaging can be used to calculate the amount of heat loss from a given system. And as you may already be aware, heating is the biggest factor in reliability of electronic components. And as you can see from the data collected by IEEE just a few years ago, the effects of temperature on the long-term reliability of power electronics were the top concerns within the green energy sector. Heating has a big effect on the reliability and lifetime of the end equipment. And reduced heating not only improves the efficiency, like we talked about in the previous slide, but it also means the equipment can be designed for operation without the use of cooling fans, which helps to reduce audible noise, which in a lot of cases can be very, very desirable. Thermal runaway has also been a concern within power electronics, but with the recent rise in the design and production of electric vehicles and other systems using lithium-ion batteries, it's been pushed to the forefront. If unchecked, thermal runaway in any electrical system can have cataclysmic effects. Luckily, with thermal imaging, having the ability to track temperature changes in real time, it can help identify and predict potential runaway conditions before they get out of hand, which is vital in protecting critical equipment and workers. And with the reduced availability of some electronics components and the subsequent increase in the price for what is available, some industry sectors are seeing a large uptick in counterfeit parts in their supply chains. As you can imagine, this is a major concern for military outfits due to the potential of the non-legitimate parts failing in mission-critical systems. Counterfeit electronic components and devices are widely available at bargain prices via the internet. And according to a US Government Accountability Office study, suspect counterfeit and bogus military grade electronics parts can be easily found on many internet purchasing platforms. And these phony devices often use cheaper materials and knockoff designs that may look like the real thing, but they have significantly different thermal signatures from the originals. And thermal imaging can actually be used to compare the thermal performance of different components and verify their legitimacy. Fortunately, the R&D and science segment at Teledyne FLIR offers a broad portfolio of thermal imaging camera systems that are ideal for a number of these electronic design and testing applications. We have solutions for someone doing design work who needs to monitor temperatures on very small components or structures, and for folks who simply want to use a system for quality assurance checks on a continuous stream of different test articles. We even offer extremely affordable thermal camera systems for repair technicians to use to quickly diagnose potential faults at a push of a button. And the best thing is, most of the camera systems are scalable. So cameras that are used for testing in the development stage can also be integrated into the production process for inline inspections and verifications. For example, the A50 and A70 research and development kits are great low-cost solutions for engineers and technicians who need a thermal imaging camera for quality assurance or troubleshooting of printed circuit boards. And since the A50 and A70 cameras are built on the same platform, they share all the same basic features. Whether it's a simple gigabit Ethernet connection, which is PoE or power over Ethernet, that allows digital data streaming into the included FLIR Research Studio software, or its small form factor and straightforward mounting, the cameras are really simple to install and very easy to use. So what are these A50 and A70 research and development kits? Well, when you combine the 3 different lens options and the 2 different camera resolutions, there's actually a total of 6 different kits that we have available. The A50 has a 464 by 348 resolution that can be selected with either a standard 29 degree or a 51 degree wide angle lens or a 95 degree ultra wide angle lens. This is the same for the A70 camera with the 640 by 480 resolution. This selection of camera resolutions and lenses offers a significantly more flexibility than a single lens choice offered by our legacy camera systems. And the option for the ultra wide field of view with a 95-degree lens really increases these cameras' ability to be used in a variety of different applications. However, be aware that all the camera versions have manual focus lenses which cannot be interchanged. So you have to select the lens you need at the time of ordering, but these lenses are fixed and can't be changed. But the benefit of this simplicity is lower cost when compared to other cameras in our overall product portfolio. The R&D kits include everything you'll need to get started. This includes the camera with whichever lens you selected, all the accessories and cables you need for connecting and powering the system. The cameras in these kits will also automatically come with the visual camera and Wi-Fi options enabled and have a 1-year license of our FLIR Research Studio software included. And since the A50 and A70 cameras utilize a standard gigabit Ethernet connection for digital data streaming, you can simply connect the camera to a computer running Research Studio and you'll be off and running. The cameras can also output both RTSP and GigiVision data streams. And the Research Studio actually allows you to select which data protocol you want to use. You can even decide to dual stream both and view the infrared and visible camera images at the same time side by side. You can even choose to blend the infrared and visible streams to analyze your electronic systems in new and unique ways. And with the Wi-Fi connectivity included with these kits, you'll finally be able to cut the cord between the computer and the camera. Using a simple ad hoc network, you can directly connect the camera to a computer or tablet using FLIR Research Studio and stream live thermographic data into the software for analysis and recording. However, connection speeds and transmission distances can play a major factor in the actual frame rates you're able to achieve over Wi-Fi, so we can't really guarantee that you'll get the full 30 hertz data when using that connection. The A-Series Science Kits are ideal for electronics applications where system flexibility and the ability to acquire meaningful data quickly are important. As you'll see in the coming slides, the optics flexibility of the science kits makes them ideal for electronics design and testing applications, while the intuitive Research Studio software included in the kits gives users a variety of different options to acquire and analyze thermal data quicker than ever before. Similar to the A50 and A70 R&D kits, all the Uncooled A-Series science kits are built on the same platform, so every camera has the same basic features. These cameras are small and relatively lightweight, especially when you compare them to FLIR's higher-end cooled camera systems. These cameras are also very easy to use and can be seamlessly integrated into existing systems. With standard gigabit Ethernet that's both GigiVision and GeniCam compliant, power over Ethernet, and remote motorized focusing, you can completely control the camera and view data through a single cable connection. There are also a number of different options and extended features that allow you to customize the camera to fit your particular needs. To make the configuration simple to understand and easy to order, we've created 6 different kits built around the Uncooled A-Series cameras. The standard kits include everything you'll need to get started, while the professional kits include everything already in the standard kits, plus a few unique options that provide even more value and system flexibility. But I'll get into that, the specifics of that on each one of the kits in the following slides. But as for the cameras, we offer 3 different resolution options depending on your exact needs. And like with the A50 and A70 R&D kits, you can even decide to dual stream both and view the infrared and visible images and the same time side by side or blend the infrared and visible data. As I mentioned, the standard science kits will include everything you need to get up and running quickly. This includes the camera, a 24-degree lens, and all the accessories and cables needed for connecting and powering the camera. The cameras in these kits will also automatically come with FLIR macro mode enabled, and each kit includes a 1-year license of the FLIR Research Studio software. If you're not familiar with it, FLIR macro mode automatically increases the distance between the camera's detector and the back of the lens, which effectively reduces the minimum focus distance for the standard lens. Previously, this FLIR technology was only available on our handheld T-Series cameras, but is now available on our fixed mount A400, A500, and A700 cameras. And having macro mode as an included option is a great feature when combined with the standard 24-degree lens. By itself, the 24-degree lens has a minimum focus distance of just about 150 millimeters. And at that distance, you get a 200 micron per pixel spatial resolution on the A400, about 138 micron per pixel spatial resolution on the A500, and about 106 micron per pixel spatial resolution on the A700 camera. But when you enable the macro mode, the minimum focus actually drops down to 60 millimeters, and you get 101 micron per pixel spatial resolution on the A400, 71 per pixel spatial resolution on the A500, and all the way down to 50 micron per pixel on the A700. This configuration provides better performance than using wide-angle lenses inside their specified minimum working distance, and it's more economical than having to purchase separate close-up lenses to achieve the smaller spatial resolutions necessary to analyze temperatures on surface mount components. And here's two quick example images of what can be achieved with FLIR macro mode. The top image was taken with the standard 24-degree lens at the minimum focus distance, while the bottom image was taken with macro mode enabled. Though it may just look like I digitally zoomed in the images, the smaller spatial resolutions and overall field of view provided by macro mode actually allows you to very easily see additional details and crisper edges on the US quarter in the image. The professional science kits include everything that's already in the standard science kits, but we added a few unique items that will provide even more value. These include a visible camera and the ability to connect to the camera wirelessly. On top of that, we added in a real close-up lens that provides per pixel spatial resolutions down to 24 micron per pixel on the A700 camera. For the cameras in the standard kit, the visible camera and Wi-Fi capabilities actually exist. We just simply didn't enable them. So if you happen to purchase a standard science kit, you always can choose to enable these features later on. You can also stream digital data over Wi-Fi into the Research Studio software, just like on the R&D kits, bearing in mind you'll have the same potential for frame rate limitations based on connection speeds and transmission distances. And as I mentioned, the A-series professional science kits also include a standalone close-up lens. This lens provides a 49 micron per pixel spatial resolution when used with the A400 and a 24 micron per pixel spatial resolution on the A700 camera. And again, since the pixel resolution of the A400 is 1/4 of the A700 cameras, they'll both have a very similar overall field of view when using the close-up lens. So when you look at everything included in the professional science kits, from the 24-degree lens to macro mode and the close-up lens, we're really providing a complete close-up inspection system all in a single package. And this is really an awesome value when you look at just the optics flexibility, let alone the visible camera features and the Wi-Fi capabilities. And here's a side-by-side comparison of the different fields of view that can be achieved with the A700 Professional Science Kit when using the 24-degree lens at its minimum focus distance, when using macro mode, and when using the separate close-up lens. By using an integrated circuit and of a wireless router as a sample target, you can really see the increased details that can be achieved with each one of these lens configurations. If you need even higher performance, we have a couple of new cooled mid-wave camera packages, which are ideal for electronics testing application where crisp thermal images, superior thermal sensitivity, and fast frame rates are required to provide the accurate temperature data necessary to make critical product design decisions. These packages give you all the advantages of the cooled infrared camera system and can be purchased with either a macro lens or a 1x microscope lens, which I'll detail in the next few slides. The best part is we have aggressively priced these with the intention of making them easier to procure without the need to go through the tedious capital equipment purchasing process. Both of the affordable cooled camera packages utilize the same A6701 mid-wave camera with a 640 by 512 format detector, which provides over 327,000 individual temperature measurement pixels with a thermal sensitivity of less than 0.02 degrees Celsius. The standard frame rate and full resolution is 60 Hertz or 60 frames a second, but you can actually sub-window the detector down to run faster frame rates all the way up to 480 frames per second. And just like with the R&D and science kits I already spoke about, digital data streaming and camera control is done over a simple gigabit Ethernet connection that's GigaVision compliant. Add to it standard calibrations up to 350 degrees Celsius, a microscope stand, and our latest FLIR Research Studio software, and you have a complete high-performance thermal camera system that is ready to provide accurate and defensible temperature data to support your testing and development needs. But which of the two different lens options would work best for your application? The macro lens is an ideal lens if you expect to have a wide variety of target sizes and need a lot of flexibility in the fields of view and working distances during testing, or if you simply want to be able to evaluate a large area to start and then focus in on a smaller area of interest. The macro lens can focus from as close as 100 millimeter all out to a pretty far distance and everywhere kind of in between, which makes it extremely useful in a number of different testing scenarios where large fixtures or probing stations can kind of make it difficult to get a camera anywhere close to the test board. And you get a 0.76x magnification at the close focus distance, which equates to a very small 19.6 micron per pixel spatial resolution. So here's a quick rundown of some of the fields of view and magnification levels for the macro lens when used with the A6701 camera system in the package. But this is just a subsample based on a few standard working distances and doesn't really account for all the different focus positions since they're nearly infinite as you adjust the focus distance. As you can see, at the minimum focus distance of 100 millimeter, the overall field of view is reduced to just 12.6 millimeter by 10.1 millimeter, which is perfect for evaluating the thermal performance of integrated circuits and other surface mount components. And with a spatial resolution of just 19.6 micron per pixel, you'll even be able to see individual bond wires and how heat conduction through traces can affect the thermal performance of the nearby components. If you're working with even smaller components or plan to simply test the same types of systems consistently, and you don't need the field of view flexibility the macro lens provides, the 1x microscope lens package option may be the better choice. When used in conjunction with A6701 camera, the 1x microscope lens gives you an overall field of view of just 9.6 millimeter by 7.68 millimeter, which is roughly 30% smaller than the smallest field of view you get with the macro lens. As a result, the per pixel spatial resolution drops to just 15 micron per pixel, which produces even crisper thermal images and provides more accurate temperature measurements when you're imaging small targets. The one watch out, however, is the 1x microscope lens is a fixed focus lens with a working distance of just 30 millimeters. This is still pretty decent distance, but I've seen some testing rigs where the probes and other instrumentation that are in place that would prevent the camera lens from getting that close. So it's just something to really kind of be aware of. And of course, if you need to evaluate temperature on mixed signal devices or small semiconductor structures, we do offer higher magnification thermal microscope lenses, which can get us all the way down to less than 4 micron per pixel. And since each of the thermal camera packages I recommend for electronic design and testing include FLIR Research Studio software, I would be remiss if I didn't actually mention some of its features here real quick. This next generation of analysis software for R&D and science applications provides a number of unique features and benefits. This includes the software's ability to run on Windows, Mac, and Linux systems, as well as supporting 21 different languages, which gives you the ability to use FLIR cameras and take data in the environment you're most comfortable working in. In addition, the simplified user interface allows you to connect, record, and analyze data quicker than ever before without the need for extensive training. The FLIR Research Studio software provides unique features that allow you to quickly and efficiently display, record, and analyze accurate thermal data. This includes the ability to connect to multiple cameras at the same time. You can even open up multiple recorded files while being connected to numerous cameras and analyze data from all the cameras and all the recorded files simultaneously on the same plot or in the same table. This allows you to quickly compare data and thermal trends. FLIR Research Studio also supports customizable and savable workspaces. You're not only able to configure the workspace the way you want, but you can also save it and open it up again later, or even share it with a colleague halfway around the world. Saving the workspace saves everything, not just the layout. This includes any files you have open, the color palette, scaling, analysis, and all the modules as well. And to keep track of everything and make sure you're creating a workable interface, Research Studio allows you to customize the layout and create unique names for each analysis module and tab you have open. There's even a wizard that makes suggestions on the overall format in case you just need a little bit of help in doing it. But one of the coolest features of the FLIR Research Studio software is the ability to perform visible and infrared image fusion in real time from one of our dual streaming cameras that have a built-in visible camera. Since you can view the infrared and visible streams separately at the same time in software, we allow you to blend those images in unique ways that provide a better understanding of the thermal characteristics of the electronic system being tested. By combining visible imagery with infrared readings in real time, you're able to reveal a multifaceted image that spans the visible spectrum. The end result is a crisp fusion of visible and infrared images that add information without removing any temperature details. You can select which ranges of temperature information you want to overlay on the visible image. You can drop in a thermal picture-in-picture window onto the visible image, or even apply FLIR's unique MSX processing to add even more detail to the thermal image. But with blending, you can even adjust how much of the thermal or visible image is being shown. That means that if you elect to dial down the thermal image in blending and look at just the visible image, all the temperature information for every pixel in the thermal image is still available. This allows you to perform complete thermal analysis, including time versus temperature plotting on the visible image, which is really impactful since most people are more familiar with how things look in visible than they are and how they look in infrared. If you happen to already have a FLIR thermal camera and haven't actually had a chance to use the Research Studio software yet, we actually encourage you to go to our website and download a 30-day trial and just try it out for yourself. We're really excited about this program, and I'm sure you'll be too. So to finish up, in the fast-paced world of electronics design and testing, the need to reduce testing times, improve product performance, and reduce overall product and testing costs has never been greater. FLIR's R&D and science camera products provide the tools to meet these goals through quick and intuitive thermal measurements and analysis solutions. With products that offer clear benefits at every price point, FLIR provides a quick and measurable return on investment. A while back, Tech Validate surveyed a number of FLIR customers in the electronics industry and asked how FLIR thermal camera solutions help them to improve their businesses. The overwhelming response was faster test times and increased savings. Of those surveyed, over 71% of the customers cut their testing and product development times in half. They show more than a 2x improvement in test times using FLIR thermal measurement solutions, which led in part to an average cost savings of over $55,000. So in summary, with infrared imaging, the real value is in the testing and identification of problems that once may have been impossible to find or at least difficult to locate quickly. For manufacturers, the return on investment are the images that pinpoint a design flaw, thus reducing test times and time to market while improving product quality. So whatever companies around the globe focus their electronics design and testing budgets on, and regardless of the industries they serve, thermography offers essential insights. And that concludes the slide portion of our presentation. We can now open it up for questions.
Thanks, Jerry. This is Marty again. Great presentation, saving customers money. That's what we're all about. Very interesting.
Thanks, Marty.
It doesn't look like there's too many questions in the queue, but there are a couple. So I wanted to bounce the first one off you and see if we can answer the question. It says, do differences in emissivity impact the temperature measurements when using a thermal camera? Okay.
Yeah, that's actually a really great question. Obviously, thermal imaging cameras are just basically passive devices that are collecting the thermal energy being emitted off a surface. So if you're doing something that's a simple like qualitative type testing where you just simply want to identify hot spots, but you don't care really how hot they are. You don't really have to concern yourself as much with emissivity. Sometimes you can do some things with image subtraction to kind of highlight the changes in temperature during the testing with that. But if you actually do want to make quantitative temperature measurements, you will have to correct for the emissivity or the percent of energy being emitted from the target that you're measuring. And the good thing about that is that the FLIR Research Studio software allows you to set separate emissivity values for each individual region of interest that you have analyzing the images in the software. So, on a populated printed circuit board, we have a variety of different components with a variety of different emissivities. You can actually set separate emissivity values for every one of those individual components. So you're actually getting accurate temperature measurements.
All right, sounds great. Let's see, next question. What happens if you have a very fast event or a quick failure that you want to monitor? How do we do that?
Yeah, so during the webinar, I kind of went over some of the more, entry to mid-level infrared cameras that we have specifically for the electronics design and testing industry. But if people have applications where they have something that's a very fast event, like maybe a very something where they're energizing a circuit and kind of expect to have a very quick failure, like the A6701 camera that I mentioned can run up a little over 400,000 frames per second. But we also do have cameras that can run tens of thousands of frames a second, over 30,000 frames a second. So if you have something that, an event that you expect to happen in the millisecond type, time domain, we do have camera systems that can achieve those higher frame rates. And also, obviously, when you're doing something like that and you have a very fast event, being able to actually trigger or synchronize the camera capture or start of the capture to that event is really important as well. So, some of our higher performance cameras, like our X series cameras, not only can run fast frame rates, but they have a variety of different inputs for triggering and syncing to external devices. But also sometimes you may not have the hardware necessary to do that. But you may not know exactly when that really fast event will happen. Maybe you're energizing something, you expect it to fail really quickly, but you don't know exactly how much energy you have to put in. So the FLIR Research Studio software also allows you to basically do conditional recording. So you can actually set up a region of interest and basically set thresholds on those regions of interest, writing a simple Boolean script within the software, and then use that as a way to actually start the acquisition. So you can have something where if it exceeds, a component exceeds a certain temperature value, you can initialize the actual recording based on the temperature exceeding that value. So there's a lot of different flexibility. So if you do have something that's very a fast thermal transient or something like that, that you need thousands or tens of thousands of frames per second to capture, happens on the millisecond level. We do have camera systems that can address that as well.
Great. It sounds like Research Studio software does a whole lot and can, pretty much. Go ahead, Jerry.
Yeah, it does. It's a very feature-rich software. I mean, I think I touched on it very briefly on some of the some of the features relative to some of the infrared and visible fusion. But there's a lot of different things they can do. And as I mentioned, if you either are lucky enough to already have a FLIR camera or just simply want to try the software out, you can do that as well by simply visiting FLIR.com/research studio. Gives you the ability to download a 30-day trial, and we also have some example files that you can utilize as well.
Great. All right, it looks like we have just two more questions, one pretty quick question and one you might want to expand a little bit on. So let's do the quick one first. It says, are thermal cameras only good for development, or can they be used in the actual manufacturing process as well?
Yeah, so I think I touched on this on the webinar a little bit. Obviously, thermal imaging cameras have been used in the research and design aspect, kind of what I call like the back of a house for a number of years. But I always look at the fact that if it's critical enough to monitor temperatures in a given test or process during the design phase, it's probably important that those are actually tested for in the production phase, whether it's actually end-of-line testing on the part being produced, or if you're actually wanted to monitor the process as it's taking place. FLIR also has a whole line of camera systems specifically for productivity and quality or automation type applications. But the nice thing too is that any of the R&D or science kits that I mentioned can actually be put in production. I think I mentioned that the cameras are GigaVision and GennyCam compliant, so they're pretty easy to integrate into most standard machine vision softwares. But also sometimes it's not just the product being produced. We have cameras that are utilized for remote asset monitoring. So in the manufacturing process, we can not only evaluate the product, quality of the product being produced, but we also can monitor the equipment actually producing the product to ensure that the equipment that's doing that is running appropriately as well.
All righty. It looks like, we still have a couple of questions. I like this. What benefit does mid-wave give over long wave? Kind of a
Yeah,
generalized question.
that's a pretty Broad question, and it's really kind of application dependent with it. One of the main benefits specifically around um, uh, electronics design and testing is with the mid-wave camera, since you actually have like shorter wavelengths than the long wave cameras, we can actually get to smaller spatial resolutions, because at some point, you become physics dependent and you can't image or measure things that are smaller than the wavelength of the camera that it's the wavelength of the energy being emitted. So there's an advantage there. When you get into some other applications, there's a variety of different reasons for it based on exactly where the peak emission is and contrast and the slope with respect to the responsivity of mid-wave versus long wave. So that's a really great question. And I'd love to speak to the person who asked that in more detail. So my contact information is on the screen if you did want to send me an email. And this is actually broadly for everybody that's still with us here on the webinar. If you do have a question that you do want to answer or you want to reach out to me directly, just feel free to send me an email at the email address that's on the screen currently.
All right. One other thing that I do want to point out for those of you that are still with us, if you look over on the GoToWebinar software overlay on your screen, you'll see a handouts section that's there. And we do have a handout in there with our CHIPS brochure. So if you want to go ahead and download that PDF, do it at your leisure. But before we kick it off and close out the webinar, there's one very specific question we have here, Jerry, and it says, what is the width of the smallest electrical trace that this imaging technique can detect? For example, is there a way to detect a hot trace of 0.3 millimeters or 0.4 millimeters? Jerry?
Yeah, that's another great question. And yeah, and absolutely. I mean, especially when you start looking at things like that are like, 300 to 400 micron in size. I think that, most of the cameras that I talked about in this webinar have the ability to attach either a close-up or a microscope lens that will get you, even on our A6701 camera with the 1x lens, will get you per pixel space resolutions of 15 micron per pixel. So I don't have the actual math on that, but so you'd basically be able to have multiple pixels on even a 0.3 millimeter or 300 micron trace. So it's very easy to detect hot spots and heat within traces of that size. As I mentioned in the webinar, we can even get down to like not just the traces on the printed circuit board, but even, we can see, thermal variations on the bond wires on an integrated circuit. So
I don't see any other questions in here, so let's pass it back to Jerry for one final word of wisdom before we let everybody go. Jerry, any conclusion comments?
Yeah, I just want to thank everyone for spending their time with us today. I think, it's been about 45 minutes, so I do really appreciate everybody attending this webinar. I know everybody's like super busy and, it's hard to carve out about 45 minutes, of time. So I really appreciate you spending time. I hope you feel it was time well spent. As I mentioned, my email address is on the screen right now. So if you do have a question that you think of after the fact, or if you want some more information, or you want to get connected with your local FLIR salesperson, feel free to reach out, at any point, and I can help you along. It'd be wonderful to talk to you as well. So again, thank you so much for your time today, and I hope everyone has a great day.
All right, that'll do it. Again, I'll also thank everybody for showing up today, and be on the lookout for upcoming future webinars that we're going to have as well. So with that said, I appreciate everybody coming, and have a good day.